So this is the proton NMR for ethylbenzene, and so we've looked at the carbon NMR already and we've distinguished some of our information. So if we look at the proton NMR for our sample, we're going to match it up to the actual compound. So this is ethylbenzene, the CH3, CH2, and so you would expect that A has 2 neighboring protons, so this should end up being a triplet. B has 3 neighboring protons, so it should end up being a quartet. There is a gap between the protons on B and C, so there is no interaction there. C should be coupled with D, D should be coupled with C and B, but they're all in the same range, so we're going to notice something peculiar about the aromatic. I see that I do have some peaks in the alkyl range, somewhere between 0 and about 4. And then 7 to 8 is where my aromatics are, which makes complete sense. I should have a couple of peaks in the, 2 peaks in the alkyl range, and I should have some peaks in the aromatic range. So now I'm going to zoom in on the alkyl range. And if you look very carefully, I do in fact see a triplet. It is the most upfield peak, and so when I look back at my compound, so now we're going to do the same thing we did with the carbon NMR. We're going to put in our peaks. So that triplet shows up at about 1.5, and the quartet shows up around 2.9. So what you notice is I didn't put a number on every single inside that multiplicity. It's not important to actually do that. What is more important is just to pick one of the peaks, probably in the middle, and use that rather than actually putting all of the values. And we're doing this because this is really just one peak. The other thing that we're going to do is integration. So if you go back, you're going to go and find your symbol that looks like an integral. So if you're in the other version of the software, it's actually open on your window already. We're going to click on that to do our integration. However, we need to be very careful with our integrations because it's telling us a ratio, and so we need to zoom in on the peak that we're actually integrating, and we're expecting that since this is our triplet, its neighbor is 2 hydrogens, we should expect that this peak, when you integrate it, should be a CH3. So the software has no idea what your molecule is. It has no idea what you're looking at. And so when you're doing the integrations, you're just looking at a ratio. So for instance, if you're given a textbook problem, to figure out that ratio, you would divide everything by the lowest number and then look at the ratio between the protons. However, the software is pretty helpful at actually doing some of that for you. So if I look at my sample, I've now integrated my quartet, and instead of just taking these 2 numbers, dividing all the numbers by the lowest number, I could actually, because I know what my sample is, this is a little bit different if you're not quite sure what this is, but because I know what this sample is, I can figure out what it should be. Typically when you see a quartet, a little bit more downfield than a triplet, and usually in the order of 1 to 2 ppm difference, a lot of times that indicates that there's an ethyl group. Not all the time, but it's a good indication. And so my triplet should be a CH3. So I can use the software to actually do that for me. So what I'm going to do is go back to my integral. I'm going to click on that peak, one that I just put in with the integral. In the software, if you go to the top left, there's a button that says options. Click on show options, and now what I want to do is normalize my peak. So I know that this peak should be my CH3, so I'm going to change this number to 3, hit enter, and notice now this becomes 3 and this becomes basically 2, which is exactly what I expected. The aromatic ring, on the other hand, I expect that there should be 5 protons on here, and so if I did this integration, we'll talk about why this, nothing that looks like very clean triplets or very clean doublets, but it's something close. It's not quite a doublet, it's not quite a triplet, and aromatic bonds are so close because of the double bonds. Remember in class we talked about multiplicities being about 3 average bond lengths, carbon bond lengths apart. However, aromatics and other double bonds are a lot shorter, so we tend to see a little bit difference here. And so instead of a doublet and a triplet, we see kind of more like a multiplet. So I'm going to integrate, and when you integrate, you click and hold and drag all the way across the peak, And I'm going to do this for the second peak. Click and drag and hold all the way across. So this is about 3, this is about 2, which it makes about 5. So I do in fact have 5 protons, which makes sense. So now that I look at my spectra, if I were to zoom in, I have a triplet, a quartet, and I have these multiplets for the aromatic ring. So oftentimes you're going to just say multiplet for aromatic rings. If you can't really distinguish what some of these peaks are, you usually say multiplet. That's what are some of the major things you're going to see for proton NMR. So another thing that we can do is sometimes peaks, if you look back at your handout and look at the J coupling, we can actually figure out what that J coupling is. So look back at the handout that you did in class and notice that there was a distance between each of the different types of peaks, and that tells us something about these peaks. And so oftentimes we're going to look at J coupling, and J coupling is just a way of looking at the interactions, what set of protons are related to other protons. So the way to do that is we actually have to select 2 different peaks on your multiplicity. There we're going to highlight those 2 peaks, make sure that they're highlighted. So here you'll see that the lines become yellow. And if you hit the J key, now we see the multiplicity is 7.57 Hertz. So J coupling, remember, is in Hertz. And if I go to the methylene, which is next to the CH3, and do the same thing, again, you see that it does work out being about the same. The Hertz is 7.57 between these 2 peaks, which makes sense because A is coupling B and B is coupling C, and so their interaction between each other is showing us that Hertz-wise that they are actually giving us that same frequency. We can also find J coupling when you're in the peak picking option, and if you scroll down you can see J coupling. If you're in version 5, more than likely the easiest thing for you to do is click the J key. So if we look at our proton NMR again, all the different things that we can do in here. So the most important one, lastly to go over this, is a zoom. You can select peaks, you can pick peaks. With the peak picker, we can do integrals, we can do annotations. So for instance, I know that this is my CH2 next to CH3, and I know that this peak was what I labeled as B on my proton NMR. If I go to methyl, this was a CH3 next to CH2. This is the peak that I labeled as A. And the aromatic is the peak that I labeled C through E. And so it's kind of hard to tell which one is which, and so I'm just going to label the whole thing this way.